All right, so this is the next section. We're talking about comparing two proportions here. So previously we talked about creating the confidence interval for two proportions. Today we're going to do the hypothesis test. So here's your general form of your hypothesis. Now technically your null could actually be equal. So again, we're still looking at the difference in the two proportions. And again, just like before, we use p. We're using p here. We're not using any p hats here, just like before. This could technically be equal to anything, really. We're going to restrict ourselves to the easiest scenario in which the hypothesized difference is 0. So we can write it like this, or you can write it like this. I'm actually going to most of the time write it this way because that's how the calculator is going to look. So I'm going to write it like this. And then your alternatives can look like this, or we could write it like this. So here we have an example. So they looked at 240 vinyl gloves for 63% leaked viruses, and then they looked at 240 latex gloves for 7% leaked viruses. So then we could do a test of this. Right now here, all I want you to do in this example here is just state the hypotheses. I don't want you to actually do the whole test just yet. So just state the hypotheses right now. So then if you look here at my notes, so here's my hypothesis. So I want to test that the vinyl gloves have a larger leak rate than the latex gloves. So I can do the P of vinyl is equal to the P of latex, and then I could say the vinyl is greater than the latex, or I could write it like this. And the vinyl is the leakage proportion for the P of V is the leakage proportion for the vinyl gloves, and P of L is the leakage proportion for the latex gloves. You can use 1s and 2s here if you'd rather, than just when you're defining your parameters, just make sure you're using 1s and 2s there as well. It doesn't really matter. And then the next one, again, the same thing. You can use 1s and 2s for the subscripts, or you can use letters like I did there. All right, when we're doing our test, to get our test statistic, we have to use that standardized formula there. So it's the statistic minus the parameter over the standard deviation of the statistic. So this is the z distribution. It's a test statistic. It's a z, just like it was when we had one sample. The statistic is the p hat 1 minus the p hat 2. The parameter would technically be p1 minus p2. However, we know that in our null hypothesis, we said p1 minus p2 was equal to 0. So I can just say minus 0 here. So technically, I could even get rid of that part and only look at this piece of it, divided by the standard deviation. Now, here's the problem with the standard deviation. If you remember before, back in chapter 9, when we were doing our one sample test, we would say, in the null, we would say that p was equal to some value. And then we would use that value in the standard deviation formula. So we would actually plug that in. We would plug in p. So remember, in the confidence interval formula, we're plugging in p hat. So the same idea is true here. In the hypothesis test, we think we know what P is, and we think that P1 is actually equal to P2. So what we think is, since we think that they're equal to each other and that there's really no difference in them, then we should just be able to put the two samples together and create one proportion. And this is called the pooled or combined sample proportion. So basically, it's just doing the count of the successes in both samples, so the x1 plus the x2, divided by the individuals in the both samples, so n1 plus n2. Now, so then what we would do then in that standard deviation formula, so how this is different from yesterday is yesterday we had the p hat 1 and the p hat 1 here and the p hat 2 and the p hat 2 here. Now we're using that combined one, just like we did when we were doing the one sample hypothesis test. Remember, it was different than the confidence interval for one sample. All right, your four-step process here. So you're stating what you're doing, checking your conditions, your two sample z-test for proportions, the random check, still check that. The normal check, there's a little note here, and I will talk about this again. So if you remember, when we were doing one samples, we would look at n times p greater than or equal to 10, and n times 1 minus p greater than or equal to 10. Remember, we switched that condition from the confidence interval and hypothesis test when we were doing one sample. So technically here we should switch the condition as well. So the footnote down here, it says it would be more correct to use that combined, that pooled sample proportion, the combined sample proportion in that check. But that would require us actually calculating it and using it and so forth. So we're just going to stick with the easier check, and we'll just keep it consistent with what we did for the confidence interval. I will show you in an example later on why it's okay for us to keep it the same as we did for the confidence interval. Technically, even when we did one sample, it would have been okay for us to still use the hat, but it's just easier. It was easy enough back then to just switch it and use the P, because the P is technically more correct. All right, then again, this is a little bit different in your notes packet than one I copied for you. So you want to make sure the samples are independent, and then you also want to check the if the observations are independent. All right, so this would be the formula for the test statistic. So again, there's the difference in the sample proportions, and then there's that combined proportion there. Again, it'll be much easier to use your calculator. If you wanted to find the p-value by hand, so if you found the test statistic and you want to find the p-value by hand, you could use that normal CDF. It would just be easy enough. In the conclusion step, so you want to change that part just like how we did last chapter. So if you're not given a significance level, just pick one in step one. So just like we did last chapter, reject or fail to reject your final piece in terms of the alternative. All right, so here's an example. Our teenager's going deaf. So in a study of, so you have 3,000 randomly selected teenagers in this year, and 15% showed some hearing loss. And then you have another group of teenagers in this group of years, and there's some hearing loss. So those evidence give convincing evidence the proportion of all teens with hearing loss has increased. Test at the 0.01 level of significance. All right, so here's my first population here. Here's my my second one here. And you don't have to write this piece right here. I just wrote it there to kind of organize what I was doing. This is where you can, just here in this first step, step one here, this is where you could denote your P1 and your P2 and which one is which. All right, so P1 is this year, this is P2. We think that the hearing loss has increased, so P2 would be greater than P1 in that alternative there. And I always just keep P1 first, it just makes more sense. There's my two sample, both of them are random. All right, the normal check. So this has been met here. So again, I'm just using that P hat here. Now for this independent check, one thing I'm missing here is I should have said that the samples are independent of each other. They should be independent. There is no way somebody who was a teenager in 1988 to 1994 could still be a teenager in 2005 to 2006. That just doesn't happen. So we should say the samples are independent of each other. They are independent, and then there would be at least this many teenagers and that many teenagers in those respective years. Here's my inputs. There's the direction of my alternative. There's my test statistic. There's my p-value. So the p-value is less than alpha. So the alpha they gave us was 0.01. So I'm rejecting the null. There is enough evidence to support that the proportion of teens with hearing loss is greater in the 2005 to 2006 years. Okay, so that's basically it. All right, so now let's just talk here about a little bit more about that combined proportion there. So the combined proportion, so if I did it for this particular example here, what this is saying is that I would combine the successes here. So in the null hypothesis, I am stating that I think those two proportions are equal. If I think the two proportions are equal, then I should be able to put the two samples together and create one proportion. So that's what I'm doing here. So this would be my one proportion here. So that which is what that combined PC is. So that is what's being used in that standard deviation formula. So if you went through and actually did this formula by hand, you would see how they come up with that test statistic there. Now to talk to you about that check, so remember I said it would be really more correct to use that P hat C there. So let's think about if I plug that in there. So if I plug that in, these are what I get, and these are all at least 10. So just like before, the condition is still met. Now let's think about this here. So this is P hat C, this is P hat 1, this is P hat 2. So therefore, P hat C has to be greater than P hat 1, and P hat C has to be greater than P hat 2. So P hat C is always bigger than those ones. So if the condition is met for these ones right here, so when we're checking, that's what we're checking up here. We're using that P hat 1 and P hat 2, not P hat C. So if the condition is met for P hat 1 and P hat 2, and P hat 1 and P hat 2 are supposed to be less than P hat C, then the condition has to be met for P hat C as well. All right, so that's all that that's saying there. So just remember that. And then the homework, it's on your packet, not on this one. So it's right here. So this is what you would want to work on right now. And then tomorrow we'll talk about the means. The end.